Now we're going to go over section 11.4, which is inferences on two population standard deviations and comparing two population standard deviations. So you may remember with one population standard deviation from chapter 10, we were dealing with a new distribution, the chi-squared distribution. Now we're actually going to be dealing with another distribution, what is known as the F distribution. So the F distribution is needed for when you have two population standard deviations. So let's go ahead and talk about some characteristics of the F distribution. You'll notice that it's kind of similar to the chi-square distribution. There's some similarities. First off, uh, we'll see that the general shape is the same. The minimum, we'll just start out with this. Just kind of a general picture. You can find this in your book. So this is for an F distribution. Like the chi distribution, it's dependent on the sample size. And since we have two different variables here, because we're comparing two standard deviations, we're going to have a sample size for each. So it gets a little more confusing. Not really confusing, but it's dependent on both sample sizes of each variable. So we'll notice that first off, the F distribution, or what we'll be using for the F distribution in this section is defined as the sample standard deviation squared of one variable and the sample standard deviation squared of the other variable. Okay, so let's go ahead and just check out the shape of this distribution. And if we think about this, what would be the smallest value you can get from this? The smallest value, similar to the chi-square distribution, is, as you may imagine, since we're squaring two values, and since standard deviation is positive anyways, this has to be positive. Well, actually, you could get 0 on the numerator, and get 0 for a standard deviation, which would give you 0 for F. So we can never get negative values. It's non-negative values are the possible values for the F distribution. But the general shape is very, very similar to the chi-square distribution. And the general idea is that as the sample sizes increase, it gets more and more normal. So it starts out, it's really extreme, like that when you have small standard deviations, or small sample sizes. And then as n increases, it moves, so it'll maybe look like this for still kind of a small standard deviation, and then it'll look maybe something like that for a little bit larger, and then eventually you'll get to something that's a little bit more normal. As n increases, it gets more and more normal. Similar to the chi-square distribution, but the idea, I should emphasize this, all these distributions have a minimum of 0. Okay, so there's no tail going off out here. It always stops here at 0. Okay, and so what you may imagine that you can see here is that this distribution is skewed right. It gets more and more normal as the sample size increases, but in general you can see it's skewed right. As mentioned before, just to emphasize again, it is similar to the chi-square distribution. It's dependent on the sample size, and that's also similar with the t distribution. It depends on the sample size. That's why we need to know about the degrees of freedom to know what distribution, exactly which row we're looking at on the t table. And also, since it's a distribution, a probability distribution, F distribution, chi-squared, and all of them are probability distributions. The total area under the curve has to be 1, which represents 100%. Yeah, so let's go ahead and just talk about some of the properties of an F distribution that you will be using here. First off, we have some subscripts. So let's just say F sub alpha. So, well, I'll get to what that alpha exactly means, but you should be familiar with kind of what it means, an idea. N1 minus 1, comma, N2 minus 2, or 1, sorry, N2 minus 1. So you have these subscripts of alpha. So the F value is dependent on alpha, our level of significance, our sample size of our first variable, and then our sample size of our second variable. That will tell you what your F value is. And so alpha here represents, similar to the chi-square distribution, it represents is the area to the right. Okay? Unlike the z distribution, which measures the area to the left, this measures the area to the right. So if we were looking at an F value here, that would have a really large alpha compared to an F value here, because the area to the right here is relatively small compared to the area to the right here, as you can see. So think area to the right. All right, N1 minus 1 represents the sample size of the numerator. Okay, N1 is the sample size, and numerator saying that whatever variable you throw up here, and it really doesn't matter which one you choose, but you just have to remember, because it makes a difference when you look it up on the chart. Because the chart, the F table actually says numerator and denominator, so you have to keep track of which one you put in where. Which population are you taking the sample from? Are you taking from the 1 or 2? Being on the numerator or denominator respectively, and that will tell you which one goes where. You'll keep in track, and that will actually make a difference of what F value you get. So sample size of numerator in this case, since we put it on the numerator, and N2 is the sample size of denominator. Okay, and that will tell you what you're looking up here. And I'm putting N1 minus 1 because it's degrees of freedom. This is df sub 1, and this is df sub 2. Okay, we're looking at the degrees of freedom on the chart, so that's what we're looking at. And there's another very interesting distribution equation that comes from the F distribution that we never really used anything like this before. But if we wanted to figure out 1 minus alpha, N1 minus 1, and N2 minus 1. So this is coming from the same distribution, because these two values here tell you what distribution you're dealing with, and then this tells you where you're looking on that distribution. So if we're looking for n, these are coming from the same distribution, just different values. And this will be useful if you are using such as a left, like this would be for an example of a right tail test, because that would be like 0.05 and the area to the right, right? And if we wanted to find the critical value here from 1 minus alpha, that would be like 0.95. We would want that would be like a left tail test. Or if we're doing a two tail test, we would want both of these. More specifically, alpha over 2 and 1 minus alpha over 2, because we want to separate it into 2. But this is equivalent to, and this is kind of goofy, but this is just how the F distribution works, 1 divided by F sub alpha, and then what you do is you just switch these two around. So now it's N2 minus 1, comma, N1 minus 1. So it's like thinking of this as being the numerator now, and this being the denominator. according to the table when you look up values. Okay, so it switches. All right, because the table only gives you really small alphas. So if you want to look up 0.95, you have to look up 0.05, for example, and switch these two around, and then take 1 divided by that and get the value. And I'll show you with an example of how this works and use all these sort of properties using this, using this with this, using this and using this essentially. All right, so that's just a quick little show of how the F distribution works. We'll use it in just a moment. Let's go ahead and figure out an example. Kind of like winging my videos, so I haven't figured out an example yet, so I'm going to find one. And I'll show you the process of the hypothesis testing. Let's go ahead and look okay. I'm gonna, just for simplicity, I trust you can find the sample standard deviation. So I'm not gonna use raw data example. I'm gonna use an example where they give you the sample standard deviation, so I don't have to calculate it and just shorten the video a little bit. Okay, so I'm gonna use number 18 on section 11.4. So I'm on section 11.4, and this is number 18. And this is on SAT scores. Okay. All right, so a researcher wants to blah, 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 blah. Okay, so it gives you all the information that we need here. And they give you some of the statistics, the sample, statistics. Do not, so what we're doing is we're comparing do not plan to apply for financial aid, and then plan to apply for financial aid. And so do students who do not plan to apply for financial aid have a higher standard deviation on the SAT 1 math score or math exam than the students who plan to apply for financial aid at the alpha equals 0.01 level of significance? All right, so there's some keywords and kind of some keywords that you should be getting used to, which is, do students plan to apply, blah, 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 blah. Where's that keyword? Have a higher standard deviation. So just to get things straight, because it's really easy to get things kind of confused, for that reason, I'm just going to start with step 1. And then I'll get to the checks in a second. The checks are pretty straightforward. I'll get to that in a second. The H0, the null hypothesis, since we're making a hypothesis on the population standard deviation of so do not apply for financial aid. So not apply equals standard deviation of apply. So let's just use N and A. Not apply and apply. An alternative hypothesis would be standard deviation of not. Now, what did it say here? It said, do students who do not plan to apply for financial aid have a higher standard deviation on the SAT than students who plan to apply? So there we go. Based off the wording, we know it's a, in this case, a right tail test. Okay, so let's go ahead and go back to the checks now that we have the null and alternative. So that makes sense. So the first check that we need to make sure is the randomness. So let's just check and see if it actually says. Oh, it says right here. She obtains a random sample of 35 students and a random sample of 38 students for each of the different variables. So we have randomness. Good. And of course, in your paper, you'll want to be a little more descriptive than just randomness. We would say based off. Well, for your actual paper, you'll be explaining why you're actually how you actually have a random set sample. Anyways, not a big deal. Let's go back to the example. So the sample data are independent of each other. Okay. Independent. And we can assume that independent. Assume it independent. We can assume that one. Yeah, of course. One person planning to fill out a financial aid thing does not affect another person's plan to make to apply for financial aid. So that's kind of obvious. I almost want to say that this is obvious. And I mean, you kind of want to think of that logic, what it means to be independent, and kind of rationalize it. The population from which the sample is drawn is normally distributed. Is there any mention of normally distributed? Well, it doesn't actually say it here, but we know that duh. As we can see that the sample size are large enough, so n is greater than or equal to 30. I'll just say n2 and n1. They're both greater than or equal to 30. So that implies normal. So we're good. Oh, it actually says it in the problem. Forget about that. It actually states at the very bottom, SAT and math exam scores are normally distributed. Normal stated. Yeah, I was kind of questioning that. Yeah, it actually says it's normally distributed. And as you can see, it doesn't say that the sample size has to be greater than or equal to 30. It just says it has to be normally distributed to the regular population. Because we're not doing a sampling distribution involving mean or a proportion, which we've actually figured out proportion is a special case of mean involving Bernoulli distribution. Anyways, then we know actually that well, since we're not doing that, we're involving standard deviation. We need it to be normally distributed. We're not dealing with the central limit theorem here. It has to be normally distributed. Okay, so that was my bad. Crossed it out. It's stated. Okay. Anyways, we can continue on. We're done with step 1. Step 2. Alpha equals, and as we can see here, it's 0.01. And you should be feeling like this is kind of redundant with step 2 at least. So step 3 would be the test statistic. And as you may imagine, we would be using that equation that we were talking about for the F distribution. You put a sub naught involving the test statistic. F naught is equal to S1 squared divided by S2 squared. Very simple. And as we can see, based off this, let's look back, it would be 123.1 squared over 119.4 squared. So let's go ahead and calculate that really quickly. Actually, I'm gonna have to run and get something real quick. 1 sec. All right, I have a calculator now. All right, so we have 123.1 squared divide 119.4 squared, 1.063. All right. So let's go ahead and figure out now the critical value. So this is where we have to apply the properties of the critical of what I talked about on the previous page. So the critical value, since we're doing a right tail test, and remember, and I'll just draw a picture, it's really going to help. I'll draw the picture now. Imagine a skewed right distribution. So what we have here is, so you can see everything. Okay, so what we have here is a right tail test. So we want to figure out f sub, so I'll point an arrow to it right here. We'll want to figure out f sub 0.01, and if with a left tail test, it would be 0.99 because it's the area to the right, okay? The area to the right is 0.01. It could be 1, all right? Pretty straightforward. And then we want the numerator. The sample size of the numerator here is 35, so we'd be looking up 34. And then we would be looking up 37. All right? So let's go ahead and figure out that value right there. And hopefully you can read this. I'm going to, so it's 0.013437. This represents numerator and denominator, okay? So I'm going to look at that really quickly. I'll leave that on the screen. Well, we'll see what I can, so you can see this. I'm going to go back to the F distribution. Let's see if I can find that really quickly. It's got to be here. Might not be in here. Pi squared. No. All right, we're going to have to look back into the tables. Oh, do-do-do-do. This is the... All right, F distribution. Now you'll notice that there are many, many, many tables. So notice that it says degrees of freedom of the numerator. So we're looking for 34 for the numerator. So that wouldn't be there. We'd want to flip to the next page. And you may need to round. Notice that. You may need to round these values here. So, so we have 30, 40. So we can use 30. That's the closest value. And then we are going to use 37, and the closest one we can see is probably 50 for the denominator. Okay, so and then of course we have 0.01, so we would want to use again 30 and 50 and 0.01. There it is, and we can see that that value would be 2.68 right there. 0.01. Sorry, 50 and 30. That will actually, sorry, that would actually be 2.1. Okay, so there's our critical value, 2.1. Let's come back here. Little confusing. It's not really that bad. So we got a value of 2.1 for our critical value, and as we can see, this is closer to the middle. Well, actually 0 is over here, so that would be more accurate to be right around there. And that would be 1.063. And this would be the fail to reject region. And to kind of think about why this would be fail to reject, think about the perfect circumstance of when you have a standard deviation. For example, you kind of have to think about this logically. Sigma, if we're saying we want to figure out if sigma, if n, I'll put n and a. If we want n is greater than a, if we want to figure out if that's true, then what we're saying here is that this is going to be larger than this. So that's going to make this really large. All right, so that's going to be really large if this is true. And so if we're doing a right tail test in this example, this is looking good, or in other words, since we're doing fail to reject of H naught, this is looking really bad if this is really large, if we're way out here. So this would be the rejection region over here. And this would be the fail to reject region if it's really small. That makes sense? And it kind of flips the other way around. If you're doing a left tail test, it's bad if you're over here. And it's good if you're over here. Okay? Kind of the same idea. You'll have something small and then something large, and it'll make this one small. Okay, so hopefully that makes sense. And in this case, we have a fail to reject H naught. Okay, so and as for the conclusion, I think you can handle it, but you would want to go through the steps of the flow chart again, and I'll just state. So we're done with step 4. Actually, step 4 is to compare this to this, and that's what we just did right here with the picture. So I don't know if you noticed, but step 4 is usually me drawing a picture and comparing them. So step 5, I'll just write right here so we're all on the same page. Step 5, you would look at the flow chart, and we can see that does the claim contain the condition of equality? No. It said it's greater than, so no. So we're going down. Now, step 2, did we reject? No, we failed to reject. No. So we're on the bottom option. So this means option 4. The bottom option. Oh, can't see that. Option 4. So you would want to state option 4, ... paste the claim in there so it makes logical sense when you read it. And anyways, let me know if you have any questions with that. But we've gone over several examples, and step 5 is almost always the same. So anyways, remember we're comparing standard deviations, so you're making a statement about the standard deviations, comparing the two in the conclusion. So anyways, let me know if you have any questions. This was just one example involving a right tail test. So just to let you know, I'll just talk through this. So we just did a right tail test. So a right tail test is involving a picture of looking at this tail over here, a right tail test. So we're going to be dealing with alpha because that's the area to the right for an F distribution, right? An F distribution deals with area to the right, so that would represent alpha right here. So that would represent F sub, the value here would be F sub alpha and then whatever, blah, blah. And then, so if you're doing a left tail test, a left tail test will be involving the left side of the tail. So we want the area over here to be alpha. So in this case, again, F distribution measures the area to the right. We would want F sub 1 minus alpha, because the area to the right is 1 minus alpha, the complement, comma, whatever these things are. Now with the left tail test, that is when you'll want to use that property of F sub 1 minus alpha, comma, dot, and I'll actually put like a square circle, equals 1 divided by F sub alpha, because we can only look at small values of alpha, like 0.1, we can't look at 0.9 on that table, so we would want to use this property, comma, circle, square. We have to flip them around. So try to use that. I didn't go over an example of that, but just use that equation if you're doing a left tail test. That's when it comes down to. This is for a left tail test. You'll be using that equation. Okay? And then for a two tail test, I'll actually show you on the next page for the heck of it. Compared. So, like always before, if you're doing a two tail test, we want to do alpha divided by 2 because we want to separate the two tails, in the alpha into two separate tails. So we would be dealing with alpha over 2 and then alpha over 2. So we're going to be dealing with the f values of alpha over 2, since it's the area to the right, dot, dot. And this would be f sub 1 minus alpha over 2, because the area to the right here is 1 minus alpha over 2, complement of that, comma, dot, comma, dot. So similar to the left tail test, this value is equal to f sub alpha, if we imagine this as being a square in a circle, f sub alpha divided by 2 of circle square, and again 1 divided by that. So you'll have to use, similar to the left tail test, this reciprocal weird thing that's going on here to figure out what the critical value will be on the left side. And this is similar to the right tail test where you don't have to use this property. So that is a two tail test. Just kind of heads up, we didn't really cover the left tail and the two tail test on the last example. So this is just a quick run through of what you would go through. But hopefully you got this down. But if you don't, please do not hesitate to just say, hey, I don't understand this. Let's go over an example of a left tail or two tail test. And I wouldn't mind going one-on-one with over the internet with you guys, going over an example. It's pretty straightforward. So I've gone over examples with other students as mentioned, and it works pretty well. So just take the time and say, hey, I need some help, and we can go over some problems. All right. So anyways, feel free to ask me questions. Talk to you later. Bye.